Welcome to the exercises for chapter 16. Now, this chapter focuses on integration tricks and techniques. These are tools that you would use when you are integrating equations by hand, using pen or pencil or chalk. These are not really tricks that are necessary when you are implementing calculus procedures on computers for applications and in particular using libraries like SymPy. So therefore, most of the exercises in this chapter are really just focused on giving you more experience working with expressions in SymPy, with integration, with visualization, conversion to NumPy, and so on. Okay, so let's begin with exercise 1. The goal here is to implement equation 22 in SymPy, so as a symbolic expression, and confirm the indefinite integral that we calculated in the chapter using the technique called U-sub, or U substitution. I will scroll up in a moment and show you this equation. And then we're going to make some neat visualizations, and it's going to be the function on the x-axis that you see here by its antiderivative on the y-axis, and that you see here. So if you draw it as a black line, you get a beautiful little logo type image that looks like this. I think it looks really nice and elegant and minimalistic. You can also use scatter plot to draw the function by its antiderivative as dots. And then you can use color scaling with plt.scatter and make a plot that looks like this. These are just two options for some nice visualization. Here we have equation 22. So this is the integral, the indefinite integral of x times the cosine of x. Now, this is a pretty straightforward function. There's only two terms. It's the product of two terms. But it cannot be integrated using the fundamental integration techniques that you have already learned about. Instead, you need to use this technique called U-sub. And yeah, in the chapter, I walk through all of this, how to pick these different terms to be u and du and v and so on. And then we solved this problem by hand, and we got the result x times the sine of x plus the cosine of x plus the constant of integration. So now we will confirm this result using SymPy. Here I create two symbolic variables, one for x and one for c, or the constant of integration. Here's the function, x times the cosine of x, and then here I'm calculating the indefinite integral and then printing it out here. And we do indeed confirm the result that I showed in the book, x times the sine of x plus cosine of x, and then we have the constant of integration here. Very nice. Okay, so here we are discretizing the function, or evaluating the function for particular values of x. I chose to run this from minus 2 pi to plus 3 pi. There's no special reason for those particular values. I just played around with the plot, and I chose a domain for visualizing this function that I thought looked nice in the plot. So that's as mathematical as it gets in this case. Okay, so here is the substitution method to get the values of the function and to get the values of the indefinite integral. And here you can see I'm plotting the function by its integral. Okay, and then here I'm using plt.scatter to make exactly the same plot, but now using a color map. And this FYI here is just going to show you a list of color maps. So you can see the various color maps that you can try if you want to see how this function looks in different color scalings. Now for exercise 2 of chapter 16. This exercise is essentially the same as the previous exercise, so there's almost no new code that you need to write for this exercise. You do need to do a little bit of algebra by hand, but what I want to express in this exercise is the important concept that different or the same function could look different in different forms. And this is something that you need to be mindful of when you are using SymPy to work with symbolic expressions and functions. Okay, so what you want to do now is the same as the previous exercise, but using a different function. So now we have equation 16.25, that's this one over here. This is the integral of e to the minus pi times x times the sine of 7x. So we have two terms here that are multiplying each other. And you'll remember in the book text, we had to go through quite a long string of tricks, of integration tricks, in order to get this to work, in order to find a solution to this indefinite integral problem. And the solution looked like this. So you don't need to scroll back up to earlier in the book. This is the problem. This is the solution. Now, what we are going to do is basically implement this in SymPy and see whether the solution also looks like this. Now, you don't need to memorize this whole thing. If you have the physical copy of the book, you can just open it up in front of you next to the computer. But for, just for right now, we can just keep in mind that there's one term here, I guess two if you include the constant of integration, and the denominator of this term is pi squared plus 49. So this exercise is really simple to solve. It's literally the same code as the previous exercise. All you need to do is change the function, and I just wrote a new line, so it overwrites this variable. Now, when you first look at this result, this seems to be different from what I showed in the book text. And in some sense, like in a typographical sense, it is literally different. This is a different expression from what I showed in the book. However, it is mathematically equivalent. It is exactly the same. And in order to see that, what you need to do is bust out a piece of paper and a pen, work through some algebra, and see how you can simplify this expression here so it's in the same form as the expression that I showed in the book. And the important take-home learning message from this part of this exercise is that when you are working with SymPy, it is possible that you will get results that look different from what you may have gotten. And it is possible that there's a mistake. It's possible you made a mistake. It's possible there's a coding bug. But it is also possible that the two sets of results that you obtain when different methods and different approaches or different software packages really are the same mathematically, and you need to do some extra algebra to confirm that they are the same. Okay, so enough of that. Here is the same plots. I do not think that these plots look particularly interesting, but feel free to disagree with me. Maybe you like these. Maybe you can come up with some better domain for visualization that looks nicer. But yeah, anyway, this is how it looks. Exercise 3 is about partial fraction decomposition. This is a method that I described in the book. It is used to solve integration problems where the integrand is a rational function. So some algebraic expression of x divided by another algebraic expression of x. Something of the form of this, something that looks like this. So you have a polynomial divided by another polynomial. Now, this is not possible to integrate directly, and so the solution is to use partial fraction decomposition, where essentially we represent this one expression as the sum of simple fractions that have only one x term in them, instead of having an x term in the numerator and possibly multiple x terms in the denominator. Okay, now here is an important note that I wrote here in the text, and I will stress it here also in this video. The code, the SymPy code that you will write for this exercise is really just custom tailored to solve this specific problem here. If you want to write some general SymPy function that can attempt to implement a partial fractions decomposition for any rational expression, be my guest, try it. I definitely support that, but that is not part of this exercise. This exercise, you will write code specifically to solve this particular problem. There are two purposes of this exercise. One is to really make sure that you understand the partial fractions decomposition algorithm by implementing it in SymPy. And two, this exercise is going to introduce you to new methods in SymPy, working with different SymPy expressions that might be useful for you in the future. Okay, all that said, Here we go. So we're going to work with this problem here that we already solved in the chapter. Now, there are 6 steps to implementing the partial fractions decomposition and integrating this function. I will go back and forth between the book text and the Python code between each step so you can see each one in turn. So step 1 is to separate the numerator. Well, I guess there's a step 0 in here, which is to implement this function as a symbolic expression. But once we've done that, then step 1 is to separate the numerator and the denominator into separate variables using a SymPy method. And then you can print out the results like this. So the numerator is 5x plus 3, and the denominator is whatever this whole term is. Okay, so this is basically figuring out how to get SymPy to take this entire expression and understand that part of it is the numerator, part of it is the denominator, and separate out those two terms. Here we have step 0. I create these symbolic variables for x, a, and b. X, of course, is our key variable. A and b are the two variables that we will use to solve for in the simple fraction. So those will come up later. Here is the function, and yeah, I didn't specifically say to make a plot of this function, but it's always a good idea to visualize functions and data whenever possible. Okay, so it looks like this. I don't know, it looks like an H, I guess. There are two discontinuities here. And yeah, you can sort of figure out what's going on with that expression. And here I'm just writing out the expression just to make sure I haven't made any typos when typing out the function in code. Okay, so here's for step 1. We use the method as numer denom. And this is a method that you call on a symbolic expression. And the outputs of this method will be the numerator and the denominator. So now we can separate in SymPy the numerator from the denominator, which is helpful because we are going to need to factor this denominator expression here. And that is step 2. So step 2 is to factor the denominator, print out the results like this. Now SymPy is going to separate this into 3 factors. The first factor is actually just a constant. It's going to pull out the number 2 as a constant from the denominator. And then we have x plus 1 and x minus 3. Now, it turns out in terms of, what we want to achieve with integrating this function, that a constant factor is not relevant. We do not want this. So we're going to deal with that later, but don't worry about that just yet. So step 2 is to factor the denominator and print out the 3 factors. The code to factor an expression in SymPy is pretty straightforward. It's the function sim.factor. And of course, we input the denominator. And this gives us a SymPy output, which is like a list, although it's not formally a Python list. And then actually, let me just show you what this looks like. Okay, I'm going to show you what this variable looks like. Den factors. And here you see, okay, so this is the 3 terms, or the denominator, factored into 3 separate terms. And then we can use .args, this method on a SymPy expression, to give us the 3 arguments in a tuple forms, as a tuple. Okay, so that's what I do here. So I'm enumerating or looping over the different terms in this factored denominator. And that's how we get this result here. Now for step 3, here we want to create simple fractions as separate variables. Now remember, we need to have these be separate variables because we are going to integrate each of these terms separately. And then, yeah, we don't know what the numerators are yet, so we leave them as temporary variables. We typically call them A and B, or maybe C and D also, if we have more of these terms. And so this is why we need the symbolic variables A and B. Now, what I have done here is absorb factor 1 into factor 2. And that's because, as I mentioned a moment ago, we don't actually care about this factor because it's just a constant. What we need is to have factors that all have the variable x in the denominator. This is also an example of the kind of thing that if you're writing a general function to implement partial fractions decomposition for any kind of rational expression, these are things you need to worry about, but we don't want to worry about them here. So we're just custom tailoring the code to work for this specific problem. Here is where I create the two simple fractions. So 1 and 2, you can see this is a divided by, and here I'm multiplying factors factors 0 and 1 are the first two factors. That is 2 and x plus 1. So I'm combining these two factors into one term. For simple fraction 1 and for simple fraction 2, we have b divided by the second or by the third factor. Okay, so that gives us our two simple fractions here. As you know from the book text, the next step is to solve these two simple fractions for a and b. Now, in the book text, I described two different ways of going about solving for a and b using by hand, using algebraic techniques. And now, of course, we can do this in SymPy. So that's what we do here. We take these simple fractions and we solve for a and solve for b. There's a couple of different ways that you can solve for a and b. You can use sim.solve separately for this expression and then use sim.solve for this expression. I am going to show you an alternative method to solve for both of these variables simultaneously in SymPy. So this might be a little bit of new code for you, but I think it will be relevant and perhaps you will use code like this in the future. Notice here, I only call sim.solve once. So we just have one call to sim.solve, and I'm inputting this expression. And the second input here is a comma b. So it's a tuple with two elements. So these are the two variables that we are going to solve for. Now, this actually, I think I will just show you what this expression looks like, and then that will help you understand what this term does. Okay, so here I am building an equality. I'm saying the numerator equals, that's the comma here. So we have the numerator on the left-hand side. And then on the right-hand side, we have all of this. So what are we looking at here? We have the simple fraction 1. So this is the function of a times the product of all of the denominator arguments. So basically times the denominator plus simple fraction 2 times all of the denominator. So the product of all the arguments, the denominator. This code here mirrors what we do by hand to isolate a and b. Okay, so now we have an expression of three variables, technically, x, although x is the main independent variable, we don't really care about that, and a and b. And so then in this code here, I say that we want to solve this expression for a and for b. Okay, so now let's uncomment this, and we can see that this solutions variable, the output of sim.solve, is a Python dictionary where we have a, it equals 1/2, and b equals 9/4. And this confirms the answers that we got when solving by hand earlier in the book. Very nice. So that concludes the algebra part of the partial fractions decomposition method. Now for getting back to calculus. So now that we have these simple expressions, we can integrate each of these separately. And that's what you see here. So what you want to do in SymPy is integrate each of these terms separately. And that will lead us to step 6, which is simply to sum them together and confirm that we get the results that we got on in the book, in the chapter, when we worked through this problem by hand. So this part is straightforward. We're using sim.integrate, and we want to integrate the simple fraction, but substituting for a the numerical solution that we got for a over here. And then the same for b. Okay, so now we have two separate integrals for two separate terms, two separate simple fractions. And of course, we know by the linearity principle of, or property of integration, that we can sum these two together. And well, that's just summing these two parts together. And this confirms the solution that we obtained in the text. Exercise 4 is a little bit of fun. We are going to explore some interesting looking functions and their derivatives and their antiderivatives. So, begin by implementing the following two functions in SymPy, f of x and g of x. You can see that they are sine of sine of sine and cosine of cosine of cosine. And I've just raised these to higher powers. So you can see the pattern here. This is sine to the power of 1, to the power of 3 and 5. And here we have 2 and 4 and 6. What do these functions mean? How are they related to some process in physical or biological world? I have no idea. They probably don't mean anything, but they're fun to implement and they look pretty interesting. So once you have implemented these functions in SymPy, you can differentiate them in SymPy. I encourage you to try writing code to get their definite integrals in SymPy, but these you will discover that these are just too difficult for SymPy to analytically integrate. So therefore, you will need to use numerical approximations to get an indefinite integral. And of course, you know all about that from the previous chapter using SciPy. And finally, you can show a lot of results looking that look something like this. So here in panel A, I have on the x-axis is, x, and then the y-axis is the function, so f of x or g of x. These two functions have interesting looking patterns. Here, I have plotted the derivatives by their functions. So on the x-axis is the function, and the y-axis is the derivative. And then we see for function f of x, this is the one with all the signs. It just keeps looping back and forth like an infinity sign here. And then for g of x, this is the one with the cosines raised to even powers. This one I thought looked like a lemon. So I just think it looks, these two functions look nice on top of each other. Here in panel C, we see the numerical approximations of the antiderivatives of the two functions. And it's interesting to see that f of x, so the integral of f, goes up and down because the function itself goes up and down. So as you are calculating the cumulative sum, it's going to hover around 0 because you have positive values and negative values. But g of x, which is the cosine function with all the positive exponents, that is a strictly positive function, or at least a non-negative function. So its antiderivative is going to be monotonically increasing. And this means that we can plot one by the other, and it just makes this really interesting kind of, I don't know what you call it, increasing square shape here like this. So we have the antiderivative of f on the x-axis and the antiderivative of g on the y-axis. Nothing super fancy going on in the code here. Here I am, well, we already have x from previous exercises, but I defined it again. And here just, this is some good reminder and practice that when you write down a trig function to a higher power, in math, it's expressed like this, or maybe I should write it like this, where the power is given before the parenthesis, but in code, it has to be done afterwards. So you do have to be a bit mindful that the powers are raised to the correct functions in the correct order. Okay, so there's the functions. We can differentiate them, no problem. And by we, I mean SymPy. SymPy can differentiate these expressions with no problem, but it is unable to determine analytic solutions to the indefinite integrals of these trig functions. So instead, what we do is lambdify and then calculate the approximate numerical approximations of the indefinite integrals. Here I'm using the cumulative underscore Simpsons function. Of course, you can also use cumulative underscore quad. There's a couple of different functions, trapezoid method. There's a couple of different ways you can get the integrals here. Okay, and from here, we just do plotting. So this is pretty straightforward, all the plotting code, just plotting f by by its derivative or by g or by its integral in the different subplots. I hope you find this exercise to be enjoyable and interesting to work through. I also encourage you to adapt this code, use different functions, make the functions look a bit different, use different visualizations. Maybe you can try plotting the derivative by the integral. So many possibilities for you to explore, and I'm very happy for you to continue exploring.